right, good morning. We are going to talk today about parts of circles. All right, so we've already talked about how you can have the going from the equation of a circle in graphing form to standard or general form, and then going back and forth. So today we're going to focus on how to talk about the different parts of a circle. So rather than the equation of the circle, we're going to focus on parts of the circle. All right, so a circle we know is all the points that are equidistant from one point P. And that P is the center, and then the distance is the radius. Okay, so that's our definition, the geometric definition of a circle. Now the diameter, just kind of a quick review, the diameter is the line that connects each side of the circle that goes through the center. So it's like a radius going in each direction and that passes through the center of the circle. So that's the diameter. And now we're going to talk about the central angle. We've used this before when we were talking about sectors. But a central angle is an angle that's created at the center of the circle, and it's using the two radii to make both sides of that angle. Now the arc, we've also talked about the arc before. Your arc is the intercepted piece of the circle, or the piece of the circumference that is cut off by those two radii. So the arc on this one diagram is the arc AB. Okay, so let me back up. The central angle, that would be the angle APB. Okay, angle APB is our central angle. And for our arc is the arc AB. Okay. Now a sector, we've already talked about a sector as well, but a sector is the area inside like a pizza slice. So the area that's cut out by those two radii. Now this is a new one, a chord. A chord is any segment whose endpoints lie on the circle. So a chord on this one is the chord CD. But if we look back at the diameter, a diameter is a specific kind of chord. So a diameter is a chord, but it's a chord that goes through the center. Okay, so if you're thinking of it as having, it's just a more specific kind of chord. Okay, so here are all the parts that we just got done talking about, just kind of outlined. So we did the central angle. We've talked about the sector. We've talked about an arc, radius, a diameter, the center of the circle, and then our new one, the chord. The chord is the chord segment CD. Okay. All right, we're going to stop right there. And then I will add a little bit more to this other piece of it. All right.
Okay, so we're going to talk about the central angle theorem. Now, we've just done another one on this part, but just kind of refresh and give some clarification. That the measure of the central angle is equal to the measure of the intercepted arc. And I want to make a special note on this, that arc length is a different measurement than the measure of an arc. Okay, that's what this is about. So we've already talked about arc length, but now we're talking about the measure of an arc. All right, so I want to use this example to kind of go over how these two things are different. So arc length is different than the measure of the arc. Okay, it's different than the measure of the arc. And if we're given a circle that has the center P, and we know that the central angle, angle APB, is 120, then we're going to look at this and say, okay, if I have a central angle that's 120, and my radius is 3 centimeters, and I'm asked the question, what is the arc length? then we've already done this before. We know that it's the central angle over 360 times the circumference, which is 2 pi r. So once you multiply that out, then we get 2 pi, and then our units are centimeters. That's the arc length. Centimeters is a measure of length. When we're talking about the measure of arc AB is going to be 120 degrees. And once again, this makes sense because if it takes 360 degrees to go around the center, it's going to take 360 degrees to go around the circle. Okay? And measure is, the units we use are degrees. If it's a length, then our units are going to be centimeters or inches or miles, but it'll be a length measurement. And if we're asked for the measure of an arc, then our units are degrees. All right, so the inscribed angle theorem is the one we were just talking about. The measure of an inscribed angle is equal to half the measure of the intercepted arc. And I'm also going to add or half of the central angle with the same intercepted arc. So it's going to be half of each one of those. And this is sometimes known as the Star Trek theorem, and I'll explain that in just a minute. All right, so if we're looking at this, we've got, we're given that the intercepted arc, or arc AB, is 80 degrees. Its measure is 80 degrees. So that means that the measure of the central angle, angle APB, is also 80 degrees. Because that's using the central angle theorem. Okay, so if this intercepted arc is 80 degrees, the central angle is 80 degrees. And now we also have the inscribed angle theorem. So this central angle shares the same intercepted arc as that inscribed angle. So that means that this angle is 40 degrees. Okay, and the reason that this one has the nickname, or they're also known as the Star Trek theorem, is because this specific diagram kind of looks like the symbol for the Federation. If you are a Star Trek person, you'd understand.
All right, so now we're going to talk about the central angle and the central angle theorem. So we've just talked about the central angle, and so now it's time to move on to what that theorem looks like. Okay. So the measure of a central angle is equal to the measure of the intercepted arc. Okay, so note that this is talking about our intercepted arc is the arc length or the distance on the circumference from y to z. So that's what they're talking about when they say the intercepted arc. And it makes perfect sense on this, because if we think about how many degrees it takes to go around an entire circle, well, it's going to be 360 degrees at the center, and it's also going to be 360 degrees for the circumference, as long as we're measuring both of these in degrees. So the measure of the central angle is going to be the same as the measure of the intercepted arc. All right? So our central angle and our intercepted arc. So on this diagram, and I know I didn't get all of it on here, but if we have a circle and we know that the intercepted arc AB is 25 degrees, then we can say that x is equal to 25. So that's talking about the central angle for x. And then the same thing down here, if I know that this is 55, I can say that the intercepted arc that would be out here is also 55 degrees. Okay. Now, if I had the whole diameter, like if I knew that this was the diameter, I could say that 25 plus 55 plus something had to equal 180, and then we could figure out why. All right, but now let's talk about an inscribed angle. So this is a new piece. An inscribed angle is an angle whose vertex lies not on the center, but on the circle itself, and that the sides aren't radii, but the sides are chords. Okay, so this would be an example of an inscribed angle. So we have, here's the vertex of our angle, and it's on the center, or it's on the circle itself. All right, so here are some examples, and on this one, we've got angle 1, and that is inside the circle, but no, that is not going to be an inscribed angle. Okay. Our second angle, angle 2, this one, its vertex is on the circle. So yes, that is going to be an inscribed angle. And then on this one, the vertex of the angle is at the center. So this isn't going to be an inscribed angle. This is a central angle. So no, this is not inscribed angle. It would be a central angle. And then we have one over here, angle 4. And this one, notice that the vertex is on the circle. So yes, this is an inscribed angle. Now, for our inscribed angle theorem, if we know the central angle or the intercepted arc, or the measure of the intercepted arc, then we can figure out the intercepted angle. It's always going to be half of the measure of the intercepted arc. Okay, so if our intercepted arc is 110 degrees, then any inscribed angle, so any inscribed angle is going to have half of that measure. So 110 divided by 2, cut in half, gives us that 55. Okay, so that's the inscribed angle theorem. So if our intercepted arc is 110 degrees, the inscribed angle is 55. All right, so now let's look at this example. So we've got a lot of things happening on this. So let's go through and identify our parts. We have angle ABC is a central angle, and angle CDA is an inscribed angle. Okay? So if I use the central angle theorem, I can say that if this intercepted arc, and I should have a degree here, but let's just say that there's a degree symbol there. So if the measure of arc CA is 60 degrees, then the central angle is also going to be 60 degrees. And now we can use the inscribed angle theorem to say, all right, if this is 60 degrees and our central angle is 60 degrees, then our inscribed angle is going to be half of that, so that's going to be 30 degrees. All right, now if we look at this one doesn't have the central angle in it. We could add it in if we needed to, but we don't need to. So we've got our intercepted arc is 85 degrees, and then I've got this other one here that is an inscribed angle, and it's not going to be 85 degrees, it's going to be half of that. So that's going to be half of 85 degrees. Now, here's another one. All I did was kind of take this point and slide it over here. So if we used the inscribed angle theorem to say that 85 divided by 2 gives us this, which is going to be, what would that be, 40, oh, this is the worst part of my stuff, 42.5. And then this one over here is going to have the same measurement. Okay, just because I moved where the vertex of the angle is, it's not going to change it. So if I've got 85 degrees here for my intercepted arc, then the inscribed angles are going to have the same measure because they have the same intercepted arc. Okay, so two angles that have the same intercepted arc are going to be congruent. So the angle here is going to be congruent to this angle here. All right, let's back out of this a little bit. And we're going to go to another spot. All right, so now we're going to talk about more parts of circles, give a little bit of clarity on arcs. So the first one we're going to talk about is the minor arc. And minor arcs are less than 180 degrees. So a couple of examples using this diagram is the arc AB. So that's going to be this arc AB. Or you could even do BC. Okay? Any arc that is going to be less than 180 degrees. If it's more than 180 degrees, that makes it a major arc. Okay, so a major arc is greater than 180 degrees, and we use 3 points in giving it its name. So a major arc on this one would be arc ACB, because it's going to be bigger than 180 degrees. And then our last one is if it's exactly 180 degrees. We call that a semicircle. Semicircle is when it's exactly 180 degrees, and you can use 2 points or 3 points in naming a semicircle. Okay. All right, now a chord is a line segment whose endpoints lie on the circle. So in our diagram, I've done this in blue, chord AB has its endpoints on the circle P. So AB, this line segment AB, is a chord of circle P. And then we've got the tangent, and a tangent is any line that intersects in exactly 1 point. Okay, so it intersects at exactly 1 point. And on this one I've done it in purple. So we have the line RT that is tangent to circle P at point R. So the line RT, is tangent because it only intersects the circle at exactly 1 point. Okay, and that point R is called the point of tangency. Okay, so R is the point of tangency. So the 1 point in which the line intersects the circle is called the point of tangency. Okay, and then we have our secant. A secant is a line that intersects the circle twice. So I've done this one in green. Okay, so we have line MN is a secant of circle P, and it contains the chord MN. Okay, so remember this, a line is going to be the secant, but if it's a segment, then it's going to make it a chord. Okay, now chords, secants, and tangents can all intersect each other and interact in different ways. Now I haven't extended any of these lines, but you could see if we extended the tangent line and the secant line that they would create an angle down here outside of the circle. Okay, so in a minute we're going to talk about how all these different lines and segments interact with each other in regards to the circle and the angles that get created with those interactions.